1665. So we have two talks today on the Hubble tension. And so the first talk by Simon Birrer is about measuring the Hubble constant, and it's an update of the previous work. So
thank you very much, Michele. Yeah, in this first half, I'll talk about measuring the Hubble constant with what we call time delay cosmography. I will go in the techniques in some details in the history and present the current updates that has quite a bit changed the landscape, I'd say. And then that is basically then for preparation. Also then for the second talk here, we'll talk about other implications that this may have in terms of dark matter science. So this is work I present on behalf or with the TDCOSMO collaboration, as well as the STRIDES and the dark energy collaboration to find strong gravitational lenses, special mentioning of PhD students that I work with. And here a montage of, say, pretty pictures of the Hubble Space Telescope of quadruply lensed quasar, which I'll go into how we can measure the Hubble constant with these type of objects. So a very brief history of the Hubble constant. So this is the one famous paper by Edwin Hubble in 1929, where he laid out that galaxies that are further away have a receding velocity that move further away from us. And that slope effectively is what we call the Hubble constant, the local expansion rate of the universe. More recently here, a diagram with supernova that extends this range to a very high redshift, and with a remarkable consistent picture of the expansion history, the relative expansion history throughout half of the age of the universe at least. So what has changed between these diagrams are a few things. So one thing is that Hubble boldly put out absolute distances here on the y-axis, on the x-axis, while this plot here, 2013, put a distance modulus. So this is an uncalibrated distance towards it. The value has also slightly changed by about an order of magnitude. If you think of like, this is 1 megaparsec, the predicted, or here the stated value is about 500 kilometers per second. So there we are down by a factor of about 7. And the units also have changed. It's kilometers per second. That's just a note on it. So more recently, so if we go, this is a figure from Wendy Freeman et al. So what is the Hubble tension? So I don't go in detail in the theoretical implication that this may have. It's not just a tension of two values. I'll come a bit into this. So in brief, historically, how this Hubble tension has formed is that the cosmic microwave background measurements or sound horizon calibrated measurements in general have increased precision and have consistently tied to a value around 67 kilometers per megaparsec. While in particular, the CFE based measurements from the SHOES team have also gained precision and have put their value around 74, 73 kilometers per megaparsec per second. And so this increased tension is what we call the Hubble constant tensions. And so now this is not the full picture. So if we have a landscape of different measurements of the Hubble constant, this is one that I dated July 7th, 2020, so which is already outdated. So the field is fastly moving. What you see here on top are these early universe-based measurements, meaning they are calibrated, so to speak, on physics of how the sound horizon expanded in the early universe, and use that as an absolute distance anchor on then interpreting the scales of the universe. While in this middle box, what I call late, are independent measurements that use different assumptions and calibrator in their study of absolute distances and scales. So this is the SHOES team. This is the most prominent advocate for the tension in terms of the precision and the value they got. Then we have here the Carnegie Chicago Hubble Key Project team around Friedman and Madore. They use a tip of the red giant branch to calibrate, and they get a more consistent value with what's quoted by the large-scale cosmology experiments. Then there are a set of other measurements. So one is using MIRAS variable stars. The MegaMaser Key project is using effectively accretion physics around quasar to calibrate, and surface brightness fluctuations as well here, so with slightly less precision. And the idea here is that constantly many measurements put their value high rather than low, as long as they're not calibrated with a sound horizon physics. And that's effectively what really is the tension. In the literature, you may quote one value, but that's generally that populations of measurements tied higher. So the questions, is this new physics or systematics? I will talk mainly now about one measurement of time delay cosmography, which here, this is outdated, but this was the value a few months ago from the HOLICOW collaboration here. And so this is really, we need more independent and precise measurements to tell how evidently this requires a change in how we see and perceive the expansion history of the universe and the physics involved in either of these experiments. So what is time delay cosmography? So if we have a source that's being strongly lensed by a foreground massive objects, in our case mainly massive elliptical galaxies, this can result to multiple appearance of the same image, in that case 4 images of a quasar. And here this is the only formula that, I don't know, not the only, but the most prominent formula that showed to predict the time delays. And so what you get is a difference between the arrival time of photons at different images due to 2 effects. One is the path difference between here, in essence, the top and the bottom path. So you have a geometric effect, and you have a potential, a lensing potential effect. You can think of it as a diffraction index. So it's the same language. Here, just caused by general relativity, that effectively the reference frame clocks are ticking differently while the photon passes through. So what this results in effectively is an absolute path that we scale that we can measure, and then we can turn it around knowing the redshifts involved, how fast the universe has to expand in between, in a nutshell. So here on the right, you have an animation of a movie of a flickering quasar, and that's what we need to actually measure time delays, and we need a variable source to measure precisely the time delay. And this is independent of distance ladder and CMB or any other probe and that has a say in the Hubble constant tension. So whatever comes out here can be, is completely independent measurement. Here another animation of one of our famous objects. Here we have a time series of a cadence of about nightly, so to speak, for almost a decade. And you see the light curves of the different images appearing in this graph, and you can effectively by eye curve shift and see what is the time delay measured between the different images. And that's the information that we use to effectively anchor the distances. So time and distance is pretty analogous. So this leads me to introduce the TDCOSMO project. TDCOSMO simply stands for Time Delay Cosmography. This is now our new umbrella organizations from the previous HOLICOW project that did the analysis on these 6 lenses. The CosmoGrail, this is the monitoring campaign to measure the time delay. STRIDES is external collaboration to dark energy survey for looking for new lenses that we can add to the sample. And SHARP is a collaboration around Keck adaptive optics campaign to constrain the lens modeling. Overall, the goal is to measure the Hubble constant to few percent precision. We have analyzed so far 7 lenses and more to come. So this is a joint effort to gain precision and also, and I come to that, revise our measurements and test for robustness. In short, what we do per lens here. So here is an example from the work that I led about a year or 2 ago. So what we have per lens is high resolution imaging, here particularly a Hubble Space Telescope, and also a 10-meter class adaptive optics ground-based telescope. This is required to learn a lot about the lensing effect that is present in the main deflector, to learn about actually the lensing phenomena that we need to know to interpret the time delays. These are the time delays here measured through different techniques on the data set. What we have here on the right are line of sight observations, so a larger field of view observation of what's going on in the vicinity of that signal strong lens that we need to know, because we know large scale structure also alters angular diameter distances, and that we need to take into account when we interpret our measurements. And so we have to correct for that or marginalize over the uncertainties that we have along the sight line. And what I will talk then mostly is stellar kinematics of the deflector galaxy. So this deflector galaxy is unresolved. We don't see individual stars, but the integrated velocity dispersion of the stars effectively moving through the potential, the gravitational potential of that main deflector can be measured. And this can be used as an additional knowledge about what is going on in the lensing effect in the deflector galaxy. And what we can do then, use this all together, doing Bayesian, and just write down independent likelihood and marginalizations. Here, just a lot of symbols that corresponds to different like nuisances that we have to marginalize over to lead then to effectively a distance measurement per lens. So in my talk from now on, effectively, I question the role between imaging data and stellar kinematics of what we get out. So this is just one slide of an example of forward modeling in action when we learn about the distortion, the strong lensing effect from imaging data. Here on the left, you see 2 different bands, colors, so to speak, of the Hubble Space Telescope. And this is a model that reconstructs these lensing phenomena effectively to the pixel level, while we simultaneously change the lensing effect and ask what kind of source structure and lens structure needs to be present, and we marginalize over it. It's quite extensive modeling effort that just goes into the imaging data. So when analyzed 6 gravitational lenses, this is the results that was put up about a year and a half ago by now of 6 lenses. What you see here is the independent measurements of the Hubble constant, individual independent, assumed independent measurements of the Hubble constant for the 6 lenses, and here the combined on the likelihood level. And so we got a rather precise, about 2.34% precision measurement, and it's high and 3 sigma in tension with the CMB inferred measurement. What I have to measure, so this is assumed that all the measurements are independent in how we do it, and it uses a specific type of a mass profile family, how we describe these lenses. And that's the note, the important thing that I revise later on. So then later last year, pretty much a year ago, we added the 7th lens into this picture. This is from Shachib et al. From the STRIDES collaboration. And this is the most precise single lens measurement of the Hubble constant. This is this magenta one, and it's very consistent with the previous one. So what we have here is a set of measurements that are all very consistent among each other statistically, all pointing out to a higher value. And now I go into, well, this is assuming they're independent and that the mass profile families that we're using are sufficient to describe the reality of these lenses. So this, yes.
Can I ask a question? Michele, is it okay to ask a question?
Please, go ahead.
Okay. Is any of those multi-source?
Yes. This last one is multi-source, so one of them. So this blue part here is at the different redshift than the quasar. So this leads to additional effects that we can learn from the lens. Yeah. So this has.
Okay. And it has 2 images?
It has 2 images, yeah. There may be part of a fourth here, of part of the source, yeah.
Okay, thanks.
Yeah. So here another illustration of what I just showed. This is the Wong et al. Measurement. And here I'm specific about the assumption in the mass profile. Here we average over a power law profile inference and an NFW, and Navarro-Frank and White profile, plus an additional constant mass to light ratio part that mimics the stellar mass to light. Now, early this year, we put out a paper where we split these assumptions and say, okay, what if we do all the inference just with one model or all inference just with the other model? And what we get out is effectively a very consistent value. So between the 2 families that we employed with the priors that we used on mass concentration, etc., this leads to consistent picture. So then this paper appeared among other papers. I have to say, I'll mention this, that criticize this measurement, that the assumptions we make may not be justified, and I'll come to that. And this paper changed the landscape a bit. Or the measurements from the 7 lenses leads to larger uncertainties, to about 8%. And when combining with an external data set, it actually moves down. It's a 5% measurements and becomes consistent with the CMB inference. And what I want to highlight here from the abstract is the contribution from the PhD students that I worked with while doing that this is the first time that we validate our approach on hydrodynamical simulations that we generate and then effectively run the same inference on those. That all these measurements that we've done, this includes the past, the current one, and what we plan to do in the future, are done blind in regard to H0 or any known or parameter that we could relate to H0. So we make all our decisions and our sanity checks and systematics check before we actually decide, okay, that's it. And then we turn on the flag on in our Jupyter notebooks, send the files, and then see what the Hubble constant is. And also to mention, all of the analysis here is publicly available. So you can go on these links, you get all the scripts, all the process data that we use to run this joint analysis, and also the software you can pip install for running it. So what has changed here? So I mentioned independence and mass profile assumption. In particular, and this is well known since many decades, that lensing phenomena has a degeneracy, which is commonly known as the mass sheet degeneracy. What it is effectively a transform of your lensing phenomena that leads to the same invariant imaging observables. So that all the Einstein ring, the positions, how the arc shape is identical, except that the profile is in a way altered that your time delay is changing. And if your time delay prediction is changing, effectively your inferred Hubble constant is changing. And what you see here is in 3D and in projected mass, which is what we call convergence in the lensing language, this is the transforms we can do, and they all look effectively, then the observables are identical, while the Hubble constant effectively is changed, each tick is 10% change in the Hubble constant. So this is a significant problem that we have, where imaging data itself cannot distinguish between families of these lines. Now we can make assumption that you think like one or two or only one of them is actually a reasonable model for the description of your density profile, and this breaks effectively your degeneracy among your assumptions. And what we effectively did is in this, from previous work to that latest one, in short, before we had a lot of assumptions and data on that mass profile, and now we weaken significantly the assumptions on the mass profile and add a lot of additional data that help us constrain and distinguish between these wiggles or this transform that imaging data cannot do. And this is particular, this term in the equations of the time.
Simon, can I ask a question?
Yes.
It's about the assumptions. So I went to many talks from Holy Cow over a couple of years where they discussed these assumptions of NFW or power law and discuss these based on external observations or external information, that these were very likely profiles. And so can you say more about, when you make assumptions, sometimes they're, oh, well, that would be very surprising if those weren't true. And other times you would say, oh, we were being not forthcoming about this. In reality, we had no really good justification for any of those.
So two things. So the assumption in that sense, they were not unreasonable, full stop, that were being made, and they were consistent with the data. So when we look at what our inference with basically getting rid of this assumption, they're still statistically consistent. The question to turn it around is how much uncertainties does it add when you do not make these assumptions?
I guess my question is, would it be surprising if those assumptions were not true?
The question is, no. The question is to what level of precisions there are true. At one point, every assumption breaks down. The question is, for me, is like how much support from the data is there for a certain precision in these assumptions.
So whatever the community had come to the conclusion of NFW or power law, are you able to utilize those priors, that quantitative information? Because I mean, it seems like you're trying to do a very hard job without the benefit of whatever the community came to the conclusion about NFW and power law.
Yeah. So it depends on what you ask the community is. So the data, we're effectively using the data that has been used in the past by the SLACS analysis that showed, okay, NFW plus composite is consistent. So this data is in this analysis in there. So,
but that's not the data on which people came to the conclusion about NFW, no?
From the lensing science, yes. So when there was lensing and kinematics joint analysis, this is the data that people came to the conclusion.
Okay, I thought there was more local data.
There is local data indeed. So that we didn't use yet, full stop. So this is only lensing and kinematics data. So whenever you read papers about whether this type of analysis or to what level they support, that is being used to our best knowledge in that sense. But local galaxies, indeed, this is not being used. This is on our to-do list, and we need to do that. The difficulties with local galaxies, as is already present in this analysis by generally using external data, is how self-similar are these galaxies. So, and local data may even be more or less self-similar than the lenses. And so there we have to have kind of like a ladder of self-similarity among the objects we're looking at. But it's definitely an approach we need to do and are starting to do, as there is more precise measurement of certain quantities. But they don't have lensing information. That's the trick. So some things are better, other things are worse in the local universe. So to continue here, so yeah, we significantly relax the assumption effectively in a way that we marginalize over any mathematically allowed range, which you may question whether they're physically allowed to that level or not. And what these profiles do and what helps is that the kinematics predictions of how the stars effectively move in this potential is changing by a couple of percent when you change lambda. So we have, when we have a very precise and reliable measurement of the kinematics, we can start distinguish between these profile families independently of lensing measurements, independently of assumption, or independently of other data, say from local galaxies and so forth. And that is the approach we choose here. It's like, how well can we learn about this family by just looking at the kinematics? Now, per individual lens, it's a very tough measurements to come up with this velocity dispersion. And so we moved to an additional external data sets where we have more of these measurements for more lenses. And this is the SLACS sample. This is touched on with Adam. So we moved to this sample of massive elliptical galaxies. They don't have time delays. But when we make the assumption that they're inherently following the same on a population level mass profile shapes, we can use this information by combining so the Einstein radius and the detailed imaging modeling effectively on the same level that we do for the time delay lenses and the kinematics, and we can add them to see whether we statistically prefer one or the other profile. Here, this is measurement versus prediction for the best fit model for all these 33 lenses that we're using from this sample. So when using those, indeed, we need to make the assumption, are they statistically self-similar? And that's what we're making in this current work. So we tested for some behavior, whether there is some trends in the data visible, and we don't see any additional trends that we didn't account. But this is not saying that if we don't see it, there may not be a difference between the profiles, but that's the assumptions we run. That's the best we could do when we think of what can lensing plus kinematics alone tell us about these profiles. And when we do the inference on those, these are effectively then the posterior, so to speak, of these profiles that we inferred from this type of data. And I run a bit out of time, so I go not into too much detail of all the contours. So this is the inference on the most prominent parameters that we're interested in. One is the Hubble constant, and this lambda int is effectively that transform in the mass profile. Importantly and crucially, it also depends on our knowledge prior and of how stars actually orbit in these potentials. Are they more radially or more tangentially orbiting? And depends on what they do in projections, they lead to a different answer and thus interpretation. So in short here, so this is the work of TDCOSMO 4. So here, clearly stating here, only kinematics constraints on mass profiles. So if you have better data theoretical knowledge to the level of precision that we require, and this second part is the important part, yes, these errors can significantly shrink. They will not expand relative to the parameterization that we have and potentially move. So this is TDCOSMO only. Here we use some integral field unit observation just for the anisotropy. And then when adding SLACS, and this is the two measurements or analysis inferences below, when adding SLACS, assuming they're self-similar with the TDCOSMO sample, it moves by about 1 sigma, and the error can shrink from 8 to 5%. So this here is and there's multiple different, so I haven't put all the measurements on it. So this is just effectively moving the HOLICOW here to TDCOSMO 4 with this relaxed assumption. So this is not itself, this measurement is self-consistent with both CMB inferred and a value of around 73. So we need to go to higher precision. So how to move forward. And I run out of time, so I cannot really tell our strategy how to move forward. But what I want to say is that this work that we've done here is effectively the groundwork for adding a lot of external information, for adding a lot of information from other lenses that we are adding, that we have a framework that we can self-consistently run through the inference. So we don't have to have some assumptions from one additional data set that we plug in, so we can actually marginalize and see how this information propagates. And in that sense, this opens up a lot of information that we can use, specifically with the upcoming ground and space-based surveys, where we get effectively tens of thousands of lenses, and provided we'll get the additional information on the kinematics, on the redshifts, we can learn a lot about this and can shrink these measurements. So we have put in some, so here's just a montage of lenses that are upcoming. We already know them. And so the team, TDCOSMO, is pressing towards adding more information to get back most of the uncertainty that we lost due to quite drastic relaxation of the assumptions when you allow for the full mass sheet degeneracy. And I don't want to steal more time from Veer, and so I'll stop here.
Can I ask a question?
Yeah, sure. Please.
Okay. So, I don't work in lensing, but it looks like from a distance, you've turned the problem around from learning about the Hubble constant precisely to learning about mass distributions and which samples are self-similar. And I guess I would have some skepticism that you would ever get back to actually measuring the Hubble constant to high precision, when you would always have these questions of, do we have self-similar objects? Or even if you measure kinematics, do we have the projection effects right? And so why do you think that you would ever get back there, given this, now that you put this, much bigger problem in your critical path?
So the problem is always, knowing both at once. So the mass profile and the Hubble constant. And that was in the past as well as now. The question is, how much assumptions do you put in? And my take on this is, as this is a very strong problem, the Hubble constant, with implications on different physics interpretation, we have to question the underlying assumptions and the precisions of those that we made. And so this means, we have to be.
To put a finer point on it, what I'm asking you is, if you find a result that is surprising, let's say the Hubble constant, wouldn't people always say, oh, you don't understand your mass profiles, which is sort of what happened?
So that's what happened. So, but what we can do is we can add a lot of measurements. And here, this is a forecast that just changed the right slide. So there is available, either in the archive or what we are going to observe, there is available the data that allows us to shrink these assumptions. So it will.
But this is with a new set of assumptions.
Yes, but new or less. So it's clearly
okay. We could carry this off online, but I'm just wondering if you could ever hold up to the level of scrutiny that would be required if you saw something surprising, when you have to make a series of assumptions about the projections and the way you relate the new kinematic information.
Yeah, so the key part here where we're hoping on is a JWST that gives us 2D maps of the kinematics. And when we can compare them specifically also with local galaxies, and we get same models that describes these data. We can be very certain about within the uncertainties that we're going to quote and have that our assumptions are not flawed.
Okay, so do you have any question?
I would have another one.
Please go ahead. Kfir.
So to Simon, so if you have more systems with more than one source, with significantly different angular diameter distances to them, can this help? I mean, for the new source, for the new system you mentioned, did that help? Because that breaks the Massey degeneracy in principle.
Yes, so multiple sources at different redshifts lead to different Einstein radius, and you have a better handle on the radial profile, and thus breaking the Massey degeneracy. Absolutely. The question is of how close they are in redshifts and how visible they are. And so far we were only lucky with one source, one lensing object that has these two source components. What we can do specifically with the upcoming surveys, well, we get more what we call composite lenses with multiple sources. And there we can learn independently of kinematics, even radial mass profile changes among, say, half to 2 times the Einstein radius, so to speak. And that information can be used as well. So we may not even be lucky to have double source planes on the time delays, but can use this analysis from other lenses. Again, assuming a self-similarity. And that's also a way to go. There isn't a detailed forecast of how much it does within the families, but it's definitely something worth exploring.
Thanks.
I see. So I think that we can move on since we are quite late. So next speaker is Kfir Blum from Weizmann that is going to discuss some interpretation of this data from quasar lens delay. Okay, thanks Kfir. Please go ahead.
Yeah, do you see the slides?
Yes.
All right. Yeah, thanks everybody, and thanks Simon. Yeah, so the discussion before was leading exactly to my point of view on this problem. This is work in collaboration with Emanuele Castorina and Marco Simonovic, that were at CERN at the time, and now with my student also, Luca Teodori. So what you saw before is basically this very interesting picture of different measurement of H naught, and that I take from this paper. And this could be a breakdown of lambda CDM, right? We don't understand lambda CDM. We don't understand what is the lambda and what is the CDM. It could be something very interesting. We just don't know. Nevertheless, from the, if you want, phenomenological point of view, let's clean it up a little bit. And let me take out of the plot measurements with the large error bars compared to those. Some of them are also not independent. And so clearly this picture is dominated by 2 main players. The first is the supernova and with different calibrations. And the second is the strong lensing time delays. Okay, so this is really a significant result from this point of view, what Simon just showed us. So one of the main players just went down in H naught. So in the first case, the raging debate outside is between different systematic calibrations of the distance ladder locally, actually. Maybe there is something interesting there for fundamental physics, and maybe there isn't. I don't know. For what Simon had shown us, though, the difference between the earlier result from the lensing collaborations and Simon's new result has to do with the shape, the density slopes of galaxies. And so it is a systematic effect. There may be nothing there in terms of basic physics, but there may also be something there because galaxies are very interesting objects. In some parts of them, they are dark matter dominated. So maybe we can learn something really interesting. So in fact, where I wanted to take this discussion is precisely where it was taken before in the questions to Simon, which is, look, these lensing systems with the time delays have a mass sheet degeneracy. And what Simon mentioned before is that the mass sheet degeneracy is not only from weak cosmological external convergence, it is also from local features in the lens, because the lensing probes just a very central part of the lens galaxy or profile of the lens galaxy. And features in the lens galaxy, in the density profile of the lens galaxy, slightly outside of where we see basically the action happens, can change the results. And this is going to be very difficult to constrain. Kinematics can definitely break this degeneracy, but then the measurement of H0, like we see here, in the result from Simon, is basically limited by kinematics. That's the ballpark that they are at. But what happens if you actually take a CMB prior on H0 and turn this problem around and ask, what do we learn about galaxies? And then suddenly we can get the full power of the lensing measurement, okay? Because we break the degeneracy. Of course, we lose the debate about lambda CDM, but maybe there is something very interesting to discuss, and I think that there is. And I think that if we are to learn really, this is, if you don't believe the early measurements of H0, then this is an example of what you can learn on the shapes of galaxies with an extra source of calibration of the redshift distance ladder or relation. So a point that I wanted to sharpen about the physical meaning of this measurement by Simon, okay, is that yes, there is a mass sheet degeneracy for lensing reconstruction, but what we seem to be seeing in the shift to the previous measurement is not the traditional, simplest mass sheet degeneracy, but it is some local effect in the density of the galaxies. Because the size of the effect is too large, it appears to be of weak cosmological lensing origin. What it can be is that the lens systems that we are seeing are surrounded by a large diffuse component in their mass. So basically by a fluffy halo, if you want, in their mass, extending to distances that are larger for when the images are happening. So there could be a core component in the density profile of galaxies. Now, if you think about it, if we take a lens galaxy, it could be complicated, it could be simple. It's for HOLICOW and TDCOSMO, these lenses are not spherically symmetric, they're elliptical, so they're not completely simple. Whatever it is, if you surround it with a large diffuse core component, then there is no way, as Simon explained, for the lensing analysis to break this degeneracy apart. And now if your core component dies off sufficiently far away from the center of the lens, but not to break the degeneracy, but sufficiently inside so as to not to affect cosmological lensing, then it's very hard to tell it apart. And you can calculate how degenerate the problem is. And you can show that if the radius of a core component like this is larger than a few times, maybe 2 or 3 times, the Einstein radius, projected Einstein radius of the system, then the lensing analysis cannot see it. Okay, so the error, the distortion of the lensing image becomes parametrically very small if the radius of the core is larger than the Einstein angle of the system. Okay, and this is not a true mass sheet degeneracy, it's an approximate mass sheet degeneracy, and it's more interesting in the sense it has something to do with the profile, the local profile of the galaxy. So what do we learn about galaxies if we add a CMB prior, if we are brave enough to do this? So we can take a system like this one, for example, from the 0435 from the previous, you could see it in the previous talk. And here it is over here. It has an H0 measurement of about 72 inferred from it with the power law profile model that the TDCOSMO collaboration took, or HOLICOW. And if you look at the surface density of the system, or convergence kappa of the system as a function of radius, then the default model of the lensing analysis would be the solid line. And you can ask, what do I need to do to this galaxy in order to put H0 to be consistent with the CMB that I take here to be 67 kilometers per second per megaparsec? And the answer is the dashed line, for example. Okay, you don't need to do a lot. You can add, you can have a very small modification. So if there was a question before, Do we have some first principle or some observational evidence that favors the solid line from the dashed line? I think the answer is no. I don't think we have any theoretical observational evidence that galaxies have to be pure power law or very simple NFW plus stars and can't have, you know, order 10% features in them. But this is, of course, I'm happy to discuss if you want. So if
That must be local information, no?
I'm sorry, it must
That
be
must
local
be,
information.
that must be derived from local ellipticals.
Yes, and I have slides, backup slides for that. And that I think it's very interesting to analyze. The thing is, it is still kinematics analysis with resolved ellipticals, and this exists. And people analyze this with various families of dark matter models, but not this one and not something like it. And as you know, by the time you consider the velocity anisotropy degeneracy for kinematics analysis of galaxies, and by the time you notice that what you need here is just a 7% effect, basically in surface density and near the Einstein radius, this is very hard for kinematics analysis. But
if you can't do it, locally with kinematics, then I don't understand how Simon's approach to do it with the kinematics of the actual lenses is going to help.
Well, it's gonna. Well, I'm happy to discuss to hear what he says. As he mentioned, even a single kinematics measurement, which is what they have for TDCOSMO, does put some constraint. It's just that the constraint is at the level of 10%, and the local analysis is also at the level of 10%.
But that's not so interesting. Yes. Okay.
So and lenses have like information. Just we know some other parts of the mass, right? If we have an Einstein radius of the local galaxies, that would be phenomenal. So.
Okay, let's discuss this in the end, but I think this is a crucial discussion, and I'm very happy to get back to it. The way I see it now, we don't have it right now. We don't have this data. We certainly don't have the theory to tell us that the solid is better than the dashed. And we also right now don't have the data. Maybe we will. I don't think it's hopeless. Let's discuss it in the end though. So that's what we need right now. And we can make this again exercise and ask, okay, let's imagine that the CMB is actually correct for H naught, and there is one value of H naught. And then what do we need from the different galaxies of TDCOSMO? I have 6 here, it's before the 7th was added. And what you find, you need a core component in the ballpark of this MST, mass sheet transformation parameters of the ballpark of 0.9. So it's a 10% effect in surface density near the Einstein radius with some fluctuations between systems. That's what we will need. Okay. So that's the first thing that we could guess that we might learn about galaxies. Now, this was before Simon's paper, then came out Simon's paper that actually added this kind of local mass sheet degeneracy to the problem. What does it mean local? Again, they allow the mass sheet degeneracy parameter lambda, but and at the same time not imposing information from weak external convergence. Okay, this is what it means in the end for them. They did not really add, well, there is some studies of what happens, what is the effect of a finite core distance or radius of the core, but they assume that the radius was far enough that they don't have to worry about. And so these are the numbers they get. And interestingly, again, as Simon said, the kinematics do constrain this local approximate mass sheet degeneracy. And they actually, when he adds the slacks galaxies, it pulls you towards 0.9, which is precisely what you need from the CMB, which is the reason that the central value for them was pulled to the CMB value, even though they had no prior on H naught. What I would say is that imagine that you did have a prior on H naught. So now the error bar on H naught inferred from lensing and kinematics is this. So it's in the ballpark of 10%, a bit better. And it's consistent with Planck. If we take Planck H naught, then the error bar on this MSD parameter is going to shrink to percent level. That's what you can guess. So you can actually learn something potentially interesting about galaxies. And another point, this 0.9 effect.
I don't think that's right. I don't think that's right what you said. You can assume a Planck prior as a comparison point, but it doesn't change the TDCOSMO analysis because the TDCOSMO analysis doesn't assume an H naught. So what you're talking about is, no, but what you're talking about is the comparison point to the SLAC's TDCOSMO analysis.
No, I'm claiming that for TDCOSMO, it's crucial that we're talking about time delays. So this analysis has time delays from TDCOSMO, and the time delays have the angular diameter distance redshift relation free, H0 floats. If you fix that, the time delay data, which are now free, are going to nail lambda with a smaller error bar around 0.9, assuming that there isn't.
No, I don't think it works that way. I think the right way to think of it, at the end, you get to compare the H0 to the Planck H0. And so right now,
that's what they did. Absolutely. That's what.
Yeah, but you're just restating that problem by putting the prior underneath.
No, if you'd had the prior with error bar, so the prior allows a sub% variation on H0. If you would have imposed this on the analysis as another prior in the analysis, the error bar on this lambda would shrink significantly.
Okay, I don't think so.
So we can discuss in the end, but
sure. Because at the end, then you lose the ability to compare to Planck because now you've used it already inside the problem. So.
Oh, I don't want to compare to Planck. I want to believe what Planck. Comparing done with. And that was your question to Simon.
Yeah, but you only get to compare it as well as it's measured. Well, true. I guess we'll have to.
I totally agree. You can.
I'm going to state that you're going to still be within 2 sigma of either option.
Either option being what? The H0?
Either option being the lambda int of 1 or lambda int of 0.9.
Okay, there I disagree, but let's discuss indeed in the end. Okay. So yeah, but just again, to avoid confusion here, H0 was derived. There was no prior on H0, it was derived. And if you had imposed the prior on H0, I think that you're going to shrink the uncertainties on the profile because time delays are going to nail another observable basically for you. And this observable can be summarized by this MSD parameter lambda.
Kfir, let me ask one more in one other way. Right now, if you take the H0 uncertainty there in the TDCOSMO analysis, to 2 sigma, you get up to 75 point something, and you're at lambda int of 1. So you're not adding any information to the problem by using Planck to compare after the fact or before the fact. There's no extra information you're adding. You could compare to Planck at the end and say, oh, I'm within 2 sigma, or you could do it at the end. But I guess I'm not understanding the extra information you're adding at this point.
It's just that there are time delays. This Slack's analysis,
but that's in there. That's in the analysis right now. You're not adding extra information.
The time delays is in the analysis, but the angular diameter distance or time delay distance versus redshift is not.
You're just moving the information from the left-hand side to the right-hand side. I just don't see the extra information.
Yes, if I add information on H0, I'm going to fix lambda.
But we're using that information at the end to compare to H0 and saying, okay, how many sigma are we off? That's the restatement. All right, I guess we still haven't seen it the same way. We can talk about it offline.
Sure, we can talk about it offline. It is nevertheless my claim, a prior on H0 would shrink the error bars on this lambda. It has not been done. We are trying to do an analysis like this now. And it includes giving up from this, at least the interpretation would be to give up measuring H0 at this point and looking at galaxies. Okay, so the shape of galaxies. Anyway, what I wanted to actually say here, so where am I on time? I'll just make a comment of why I think mass profiles that actually do have this kind of approximate MSD or core MSD value are actually physically very interesting. And so the thing is, this kind of profiles don't have to have anything to do with dark matter physics. The radii in the galaxy we were talking about are in fact baryonic dominated. And at best, even if you go a factor of few outside of the Einstein angle, baryons are still an order 1 effect. So it is very hard to simulate these profiles. It doesn't need to be dark matter physics, but it could be. And I'll give you one well-motivated example to my mind, which has to do with dark matter. So just in really 5 minutes or 4 minutes, and then we can discuss the question of H0 prior. So it is completely possible from the theoretical point of view that dark matter just happens to be axions. Axions or axion-like fields are very well known in many models of field theory, could be coming from stringy completions of field theory. At the moment we have one, we might as well have several. The universe easily can populate the dark matter sector with these axions if they exist. So the mechanism this works, the simplest one is called vacuum misalignment. And the simplest vacuum misalignment mechanism would tell you that if the axion physics is in the gut scale, then you're going to have relic density comparable to what we see today if the mass of your axion is very light, of the order of 10 to the minus 20 electron volt. And this is the parametric dependence. Now I'm going to go through this very fast, but these very light fields as dark matter are a very hot topic recently for various other reasons. And so they've been simulated. You can put this model on hydrodynamical simulations of galaxies. And we now understand very well that galaxies with this kind of ultralight or axion dark matter actually contain a core. We understand a lot about this core. So we understand that this is an energy minimizer at fixed mass. We think we understand why it forms. Different simulation groups, which are the data here, all agree with the profile of this energy minimizer that we can compute. There is one parameter, which is the mass of the particle that we don't know. If you give me the mass of the particle, we know the solution, and different simulations agree over 2 orders of magnitude in density. So it's an object we understand theoretically pretty well. In fact, there is some reason to think we understand even how much there would be of it. So we understand the shape of this core object, if dark matter is axions, but we also understand how much mass there should be in it. And what we are seeing from simulations is that the amount of mass in the core is such that the profile is approaching isothermal. So kinetic energy density in this core object is equal to kinetic energy density in the host galaxy. So this is what was seen. All the simulations looked at axion mass of 10 to the minus 22 electron volt or so. Now, what we're going to be led to are much lighter axions than that, not 10 to the minus 22 or 10 to the minus 21, but much lighter, 10 to the minus 25. They can still, from theory point of view, easily populate the universe with some fraction of the dark matter. They can't be all of the dark matter, okay? So if you're looking for an ad hoc aspect of this, it's definitely there. Whatever explains these lensing things, if it has to do with dark matter, it's not all of the dark matter, but it could be. How much there could be? So from cosmology, Lyman alpha, for example, and CMB at these masses, we know that it can easily make up a few tens of % of the total dark matter relic abundance, but it can't be all of it. Now, if we have this kind of ultralight axion, what do we know? What is it going to do? So we know that it's going to make cores in galaxies. We know that the radius of these cores is going to be larger than those that have been seen in existing simulations because the mass is smaller, which pushes the radius further out. And we know that maximum entropy, if you want, seems to be driving it into this relation. So the kinetic energy per unit mass in the core and in the host galaxy is comparable. Dynamical relaxation time could be a bottleneck. So if these axions exist, they would try to make a core. How does it look like? So this is a typical TDCOSMO fit for a galaxy with NFW and stars. So NFW from, again, inspired by what we see with pure N-body cold dark matter simulations, and stars fixed by the light with constant mass to light ratio. And I just arbitrarily put the H0 to be 74 in here. And for comparison, I put the position of the projected Einstein radius for this system. Okay, so you can see what I said before. These Einstein radii sit in places where baryons are dominating over the dark matter. Okay, so these are somewhat messy regions. What happens if I have this axion I was telling you about? Well, it's gonna make a core. If you tell me the mass, which I fixed it to be 10 to the minus 25 or so, I know the shape of the core. And it looks like it was drawn out of these core models that Simon had in his games with TDCOSMO data. Okay, so this is coming from the model. This is what axions are going to try to give you. And just in a few words, I can ask, does the amount, and in fact, I chose how much axons, how much core should be here, again, to fix H0 to be 67. If you ask physically, does it make sense? Well, kinetic energy per unit mass is comparable to that of the halo. It's on the low side. If this axion would do what the simulations tell us it wants to do, there would be a bit more of it, in fact. On the other hand, I can calculate the gravitational dynamical relaxation, how much of the system had time to coalesce into this axion. And here, it looks like it's limited. The mass in this axion that I chose is a bit more, but of order 1 of what the dynamical relaxation time constraints tell me. So this is a reasonable situation. If there is a stringy axion with this mass, and it's of order 10% of dark matter, it's not a fine-tuned scenario. It is definitely an ad hoc scenario, but it's not fine-tuned. And it would make a core that could look comparable to what Simon is looking at. So from this point of view, to me, very interesting if we could detect this kind of phenomena with a prior on H0 from the CMB. So I'll skip the details of what we can say about these systems, and I'll just go to summary. The lensing H0, like it was discussed before, is a measurement of galaxy, of some moments of the mass profile of galaxies at the percent level. The accuracy of the imaging data surpasses what you have right now from kinematics. So it's a first ever in a way. And so it shouldn't be a shock if we find something new at the few percent level. It's a new measurement. You can find something totally new about these galaxies. If you add a core to density profiles like the ones from HOLICOW, it's an approximate mass sheet degeneracy. If there is a 10% or so of that component, it can solve the lensing part of H0 tension. It could, in principle, be dark matter dynamics, and then it could be very interesting. I believe that a prior, an H0 prior on the lensing analysis would nail that family of lens models to very high precision. And axion's dark matter is one of the monsters that could be hiding there. So if you were thinking about early dark energy for H0, this is also very exciting to me. And it's another thing that potentially is hiding around the corner with these new measurements. So I'll stop here.
Thanks, Kfir, for this nice presentation. Do you have a question?
Kfir, I wanted to,
Yes, of course.
I wanted to apologize. I think now I understand, and later in your talk, you were talking about, I thought you were talking about simultaneously using the constraint from the CMB to see if lambda int is less than 1. You're actually talking about fixing it to the Planck value, which is the information that gives you extra leverage.
Yes.
Of course, I guess one thing I might push back on is it's not going to be the most economical result to suggest that the lensing obeys the early universe result, giving you this potential Corey axion result, because that doesn't have anything to do with the local distance ladder measurements, and so you still have to deal with those as well. I guess I would wonder why ultimately you wouldn't use the best local information to fix the lensing and see what you get out of the core profiles.
Absolutely, fair point. I mean, you could repeat the same exercise, for instance, with any of those measurements of H0, or hopefully when the dust settles and we know where we sit, maybe we have a breakdown of lambda CDM and we can choose, and we are led to look at a different H0, right? Then the message from the time delay cosmography might come out different. I'm toying with the possibility that the true H0 is from Planck.
Sure, no, I think it's a very useful exercise to say, what if I assign the lensing either this H0 or that H0? What does it say about the core profiles?
So for you, if you want, from the point of view of say, advocate of the type 1a measurement, for example, I think it's a totally valid point to say the minimal assumptions, Hernquist plus NFW, and 73 for H0 is a perfect fit for lensing and time delay, which I guess was always the point. It is a valid point.
Okay. Vivian has a question. So please, Vivian, speak.
Vivian doesn't seem able to speak, but I do see.
Okay, no, otherwise I can read the question.
Yeah, you could read this question.
It's fair to say that the TDCOSMO requires some kind of new physics, or could everything be explained within lambda CDM plus baryonics physics?
Okay, thanks very much for this question. So I think it is, in fact, while it is very amusing to consider this dark matter model, it's good to stay with our feet on the ground. The short answer is, I think it could definitely still be baryonic and dark matter physics. Simon can comment if he thinks differently, but just to tell you where we live, okay? So here is this victim system that I plot, and the two models that you can play with. So where are we, okay? So Einstein radius, projected Einstein radius is just a projected distance where all the images fall. That's RE. And here you have this system in the table. And so in this case, it was 1.2 arcsec, okay? So that's roughly the distance to where the lensing constraints are the tightest. Now, in the lensing analysis, when they have done an NFW fit to the measurement, then theta S is the projected RS, okay? The NFW scale radius. And here is where it is. It's way outside of where all the information is, okay? So what does it mean for a galaxy? I mean, how well do we understand these galaxies in terms of baryonic and dark matter physics? You know, I look at the nearest galaxy I have. It's not the right type of galaxy, but just to get an idea of what's going on, let me look at the Milky Way. It's a disk galaxy. It's not elliptical. It's different, etc., from various ways, but we have it measured to death, okay? And here is the mass profile of the Milky Way, roughly, that we get just from the circular velocity, basically, of the Milky Way. It's a spherically averaged mass profile. In fact, it doesn't look, if you just consider the spherically averaged mass profile, it doesn't look vastly different from these ellipticals, okay? If you forget that you just average the disk. So here is where, if you go ahead and put the Milky Way at a gigaparsec away and ask what would be the lensing system look like? Well, RS for the Milky Way is here at around 10,000 parsec. The Einstein angle, if I would make it a sister of this system, would be here at 1 kiloparsec. The dashed line is an NFW fit to the Milky Way. Okay, so this is an NFW fit with all of the huge amount of data that we have. And as you know very well, it's a great fit outside at tens of thousands of parsec, but inside of the Milky Way, it is a very poor fit. Rotation curve goes up the dark matter only curve. Nobody is shocked because these are stars and some gas. Okay, so all of this is stars, and the lensing information and all of this conundrum we are working on is somewhere in between. Okay, so you need to modify the mass profile compared to some guess of what stars do, tracing part of the luminosity, what we see only, and some guess of what dark matter does, and we need to do it to, you know, to a few % level. So it's good that we have many different systems. It would be fascinating if we have multiple sources and we can break the mass sheet degeneracy, but until we have more data, I would say we are not sure that we need new physics. So Simon can add, I mean, the ellipticals they're looking at are simpler animals potentially. Hopefully not just simple because they're so far away.
Well, yes and no. So we looked at hydrodynamical simulations that are currently available. And when we mocked up lenses with hydrodynamical simulations, we could rule them out to represent the universe, regardless whether H0 is 67 or 73. And the first thing is, like, there's moving scales, so the lack of resolution at the scales that were put into the hydro. To be fair, the design of the hydro were not to get an accurate description of a mass profile to 1%. Right. It was never a requirement of these hydros. And this is a tough simulation challenge itself. So do we really know with feedback? So you may get as many answers as to as many simulators you're talking to, but that's definitely something we want to intensify and see whether there's a unique predictions of those.
Yeah, sounds to me sounds hard. Another point that's important is that you have the light profile nailed fairly well, I think, for these lenses. But then again, if you look at the Milky Ways, maybe an evil example, but the mass to light is not constant for the Milky Way. It could change definitely at the level of tens of percent as you go farther away. And all of this is, I believe it's not going to be, nobody is going to claim a detection of these axions based only on this. This could be an hit that narrows us down on the track of something super interesting, but it's not going to be enough.
Thanks. Do you have other question? There is another question I can read. Can primordial black holes as dark matter can play the same role like axion to remove this H0 tension for both?
If you think they make a core, then for some reason...
Primordial black hole. Can you read the Knockfear by yourself?
I wasn't, let's see.
If you have the chat, can primordial black hole as dark matter can play the same role like axion to remove this tension?
Right. So, I mean, what the thing with the core, why I like this core, I hope we'll be left with detecting some evidence for the core. Why I like it is because mathematically it's very clean. It's not relying, I mean, it acts like a mass sheet degeneracy approximately. And this, so it works for the image to, in principle, arbitrary precision, even if we have extended host information like here, and the object is not spherically symmetric like here. So no matter how complicated the lensing information is, a core will work very well. So hopefully it's the cleanest solution in a way. So I like the core. I hope we'll be left with the detection of a core, whatever the source of it is. And then the question for you is, do your primordial black hole arrange themselves in a core distribution around the galaxy? If I would need to guess, they would look like collisionless CDM and they would have a cusp, and that's not what you need here. You need some core. Axions, ultralight axions automatically give you a core. So I see there was a question about dark matter self-interaction. So a component of dark matter with self-interaction is another natural guess. I think the answer may be yes. You want something that tends to give you a core. That would be a clean solution to this.
Fair, I have a question.
Yes.
I'm still trying to be economical with our new physics or somewhat new physics. So you could have dark matter self-interaction or something like that to produce the core. That's great. It's also, though, been suggested as something to shift the sound horizon in the early universe. I'm still looking for ways to solve the type 1a supernova distance ladder results, or the masers, or things that are local. Can you then imagine one piece of new physics like dark matter self-interaction that does both?
Well,
the core and
you don't need to. So if you have made a way to shift the sound horizon, then you are consistent with the Cepheid calibration for the supernova. And we already know, well, up to the kinematics analysis, Simon's measurement is consistent, as Simon said, is consistent with both.
Yes.
Right? So up to this kinematics analysis, you're consistent.
I see. Yeah, that's a good point. So you're saying you only need only one new physics then would do it that way. That's right.
So in a way, my new physics is doing worse off than something like that, because at least if you find a way to zoom in on the correct calibration of the distance ladder, the nominal error bars on the supernova are smaller than right now on the lensing.
Well, I guess somebody could argue something in between, and I'm not arguing this, but you could have some amount of this dark matter self-interaction that's giving you some core, not as much as you're saying, but enough to, push TDCOSMO to, I don't know, 70 or something, and, everything else being consistent there. It could be, I guess what I'm saying is it can be one piece of new physics that is affecting both sides somewhat.
Possibly, but again, my game was,
Yeah.
I don't think I have much game without fixing H naught from someone.
Yes.
And by the time you fix H naught to 73, we are going to, this would lead us, from my point of view, to some new constraint on the structure of galaxies, and we can try to rule it out. Right now, it's not easy. It's not clear that we'd be able to do it.
Okay, thanks. You have time for another question if there is.
I have a question. So in the case of self-interacting dark matter, so does that also have to be a subdominant component?
I was just guessing, though, that it needs to be a subdominant component. I did not do the analysis. And again, this is a model that naturally can give you a core that, in principle, you have a new parameter, sigma over m, and it fixes the size of the core, and the core in principle could be large. So I mean, my guess was that the sigma over m you would need is maybe incompatible with other constraints, but I haven't done it and I don't know.
One thing.
I will actually, let me add something. Maybe someone was about to say it. You cannot kill the cusp completely. So there you go. So it needs to be a subcomponent, right? We know that you need something NFW-ish in the, around the Einstein radius. What we are doing, we're not removing the cusp profile in the TDCOSMO analysis. We really have to add something to it. So you have to have this cusp component in addition to stars, and you want to add a subdominant component that's a core. And so if all of dark matter would be self-interacting, it's going to kill your entire cusp, and that's not going to be a nice solution to the problem. So now we know it has to be a subcomponent.
At the end, what matters is the total dark matter profile. You can think of like having whatever the fiducial NFW is and adding a physical core, but that doesn't need to necessarily be the interpretation. You can also just, quote unquote, alter the mass concentration relation in certain means that effectively is.
So Simon, I want to come back to this question of whether, Kfir has described this sort of theoretical framework, and it's just not obvious to me that the kinematic information you're going to collect will be enough to solve the mass profile information in an assumption-free way so that you will get back to measuring a 1%, 2% H naught.
So this is mostly what I'm just talked about, was the interpretation of what this core component means. In terms of the overall density, how it looks, that is impacted by the kinematics. And so,
yeah, but not without assumptions, not without new assumptions.
Well, it depends on which assumptions you make.
That's
so,
assumption.
I mean, every measurement has its assumptions in there. If you go somewhere.
Yeah, but these are theory assumptions. These are assumptions about the structure of galaxies, which is hard.
Yes. And so now you could come and say like, okay, you assemble the 5 different Hydra Sims group and, blindly give priors on how mass profiles look like, and you can fold them in, for example.
If they have the right axion physics in their simulation.
No, just CDM, we're not need to go exotic in the first step in measuring H naught. Right. So if you trade exotic dark matter or H naught, I would not go both ways at the same time. It may be the solution, but I think it's reasonable you choose one approach and see whether you're getting into discovery space. You can do both exercises. In that sense, our focus will remain of what are lambda CDM predictions of massive elliptical galaxies. How reliable are they to the precision we require for time delay cosmography in that second part. So if you plot a log-log plot of a mass profile and you look at the thickness of the line, that's what we need to get to 1%. And so there within these profiles. And in that sense, it's actually, I think it's remarkable with the data that we have of the kinematics, that we can effectively distinguish a 5% shift in this profile, which is really little with the data that we have in the kinematics. And so what we did there is in the hydrodynamical simulations, we employ the same kinematics modeling on mocked up, effectively projected maps, and did run the inference. And we got the right answer within the precision that we had. And so these reliability tests on simulations is valued, even though when we don't trust the simulations to the level. We can deal with the complexity, and the assumptions we currently make are not too far off to get back what we initially put into the hydrodynamical simulations. And so for me, it will be two-pronged. It will be when we gain in precision, we have to do the same validations on higher precision simulations and more of them. And so if we can show that in the same time, we can increase the reliability of our analysis on simulations, and at the same time making measurements of H0 to ever increasing precision.
Yeah, I mean, the flaw in that sort of way of thinking of it is if you had done simulations previously, but within an NFW power law framework, you would have said, oh, we recover those quite fine. I mean, what we're talking about are things that are outside assumptions in areas, for example, if you introduce axion physics or many ways to produce a core and your ability to actually see that. And that's, I just don't want to end up in the same situation as a couple of years ago where you make a different set of assumptions and then you say, okay, we have this result, but those assumptions again are the limitation.
So we don't really need a core. So if you go talk with some hydrodynamic simulation, some feedback process of the baryons or a change in the mass to light ratio of how things form can potentially lead to these effects on the overall mass profile, basically the green line here in or the joint black line as Kfir here shows. And
right, but they won't touch the microphysics of dark matter.
No, they won't.
No, yeah, I'm not sure. Simon, correct me if I'm not sure this is really answering the question. So I totally agree with you. We don't know what H0 is, right? But so it could be that H0 is 67 and feedback causes some mass from the green line to, to bulge out. And this acts effectively like my total black curve and H0 is 67. It could be. But it could be that after you run all your hardware simulation with and without feedback, you'll get 73 within what you think is lambda CDM. And then will come somebody like me and tell me, hey, add an axion to the simulation. And H0 is 67.
Exactly. That's much better, stating it much more clearly than I did.
Yeah. So currently in the way we parameterize the mass profile families, we don't rely on interpretation of whether this is axion or feedback or a different mass normalization or a different mass to light ratio or a different mass concentration relation of the selection effect of the lenses. So we don't, because it's empirically, we put in these models empirically and constrain them with data. And they're designed by design very crazy conservative in terms of having a full MST, which I totally agree. If you have a transform of lambda 0.7 or you change H0 by 30%, at one point we know it's getting unrealistic and everyone would agree with it, or most people, I'd say. But the question within 10 or 20%, that's I'd say not a closed thing. But I think the good thing for me is we have our homework to do, and this work is just the first that triggers a lot in different directions, but we can get back. And so if you're the first one to change, and specifically, and I don't disagree on that it's a significant change in the in the assumptions, and it may hold to shrink at at a higher precision at the lower H naught, but it may well move back of what is statistically allowed. And if you're the first one, you always have the risk, that you oversee something. If you go if you take away the assumptions you previously made and replace them, there are short-term risks involved in that, and I don't deny that. And so,
Simon, no, I think what I'm getting at least is going forward, if you end up finding a result that draws scrutiny because let's just say for argument's sake, you end up with 73 again, and it doesn't agree with the early universe. And let's just say for argument's sake, you were the only measurement of the late universe, right? You might say, oh, it doesn't agree. This is evidence of some physics, between the late universe and early universe. But people like Kfir can come along and come up with, probably 23 mechanisms, because he's very clever, of ways to, produce core without effects on kinematics or some of the other observables with, dark matter microphysics. So I'm just wondering going forward, whether your results would be robust to those kinds of things.
So, okay, well, I cannot predict what Kfir or others will do with the data.
Well, he's told us already, he's shown us.
Well, but the question is with increased precision on data, right? Whether he will find with increased precision on data when you shrink this far.
I just haven't seen from what the measurements you're talking about doing that it will really limit the range of options for dark matter microphysics and some of the other things, feedback and whatnot.
So at the end, whether it's microphysics or feedback doesn't really matter for the sake of H naught. So as long as the kinematics tells us reliably what the total mass shape is, specifically if we have spatially resolved kinematics paired with lensing analysis of a lot of lenses that we can see, okay, control those.
How fine a scale of spatial information would you need?
About 0.2 arc second. So we need to resolve basically between 0.1 and 2 times the half-light radius, which is about, a bit further out than the Einstein radius. Effectively, JWST in our forecast does a great job if we have like 5 hours exposures on those, to have the radial profile out to
At what wavelength? At what wavelength is that? Because you lose resolution with JWST at some point. What?
Well, it's in the infrared. With the ones that we are proposing right now, we get to about 0.2 arc second resolution, which is and also then the IFU patterns that we put on, and that will help a lot. The measurement is also in that sense difficult because there are these bright quasars just next to it that shine a lot of photons on the plate. That makes it hard on the lenses with quasars. JWST can do that, and for lenses without quasars, we can even do KCWI or other instruments that have less resolution, but then we can trace to lower signal to noise or to lower surface brightness further out. And there, effectively, the wish would be to go as far out as possible, because there, these wiggly loops that Kfir and I are shown, they become more prominent in terms of how the kinematics actually acts, also even in projection. So that we put in simulations that show that. If you have a single aperture, you cannot distinguish the wiggly type. You can just distinguish the normalization in the center. But that is the main thing that matters for the overall lambda transform. But if we can do next order wiggling corrections, that can help a lot.
Okay, thank you very much. So I think that we are Yes, quite late. If there are not other questions, I think that we can close session. Thank you very much to all of the speaker. Thanks.
Thanks very much.
Bye-bye.
Thanks, Simon.
Thank you. Very interesting.
Bye.
Bye-bye.
Bye.